Hello everyone, welcome back to our lecture series of GATE in Data Science and Artificial Intelligence. In this lecture, we are going to discuss about informed search strategies, okay? And in that specifically, we are going to discuss about greedy best first search algorithm, okay? So up till now, we have discussed all the algorithms related to uninformed search techniques. Now we are going to start with informed search techniques, right? Now let's start the session. Now, first, what is informed search, right? So basically a search strategy that uses problem-specific knowledge to find the solutions more frequently, right? In the case of uninformed search, we don't have any problem-specific knowledge to find a solution. But in the case of informed search, we have some specific knowledge regarding the goal state, right? So this is what informed search is. So we have discussed this already in the initial lectures, but what's the difference between uninformed and informed search, right? So what do you mean by this problem specific knowledge, right? So what is this problem specific knowledge, right? Now, now this informed search is also called as heuristic search, right? Heuristic search. Now, why heuristic? We'll discuss that. Okay. Now, let us take a simple tree, say simple binary tree, right? So, suppose this is my start node, this is my start node, this is my goal node, right? If we use TFS, what will happen? We start from this, we'll take either of the node and we'll try to explore each and every path and then we backtrack if we didn't found. In the case of BFS, what we'll do? So we'll try to search level by level, like explore all the nodes, and we will see whether we got the required goal or not, right? So similarly, in the case of DLS or iterative deepening depth first search, we follow same strategy, but we just put some limit to that, right? In the case of DLS and in the case of iterative deepening, we just increment the value of and limit, right? So that's the thing. But in all the algorithms, we do not have any information about this particular goal. We are trying to explore each and every goal, whatever comes under our search, right? So this is about the uninformed search technique, right? Now, in the one of the video, we have discussed about uniform cost search, right? We have discussed about uniform cost search, right? This is cost search. Now, in this search, what we do, we follow cumulative cost, right? We follow cumulative cost from start node, right? From start node. This is very important, right? Suppose if the path cost of this particular say A and B is 1, 2, 3, 4. Now in order to reach S to B, it will require me 2 units. Now in order to go from B to G, it will require me 2 plus 4, that is 6 unit, right? Because it is cumulative cost from the start node, right? From the start node. In all the uninformed search strategies, we do not have any information about the goal node. We only start from the start node. And in the case of uniform cost search, we use this cumulative cost function that is also from the start node, not from the goal node, right? So up till now in the uninformed search strategies, we don't have any information about the goal node. Now what happens in the case of informed search? Suppose same graph I will take, okay? Same graph, okay? This is my goal, this is my starting. We have some knowledge about this particular goal. So like in which direction this goal belongs, in which direction this goal lies, or what is the distance from this particular node to this particular node, what is the distance from this particular node to this particular node. We have some kind of information about the goal state, right? Not about the start node. We don't have any information in the case of uninformed strategies about the goal node. But in the case of informed search, we have some information about the particular goal state. And that information or that estimate, we can call it as heuristic. Okay. We have some information about a particular, we are predicting or we are just guessing, we are guessing based on the problem specific knowledge that our goal may lie in this particular direction. Okay. For example, this is my 2D graph, right? This is x-axis, this is y-axis, and this is my starting point. Suppose I know the distance between B and G and A and G, okay? So if I go by B and G, it will take me around say 5 unit, and if I go by A to G, it will take me around say B to G 5 unit and A to G around 7 unit, right? Now we have some particular information that if I go by this particular path, it will take me less number of time, or you can say unit, right? Either in terms of time or cost, right? But it should be a lesser value, right? So basically we have some specific information about the particular problem, right? So this is what informed search is. So we'll discuss more about this heuristic things, right? Now, what is best first search is? So, best first search is an informed search strategy that select nodes for expansion based on the evaluation function f of n, with the lowest evaluation being expanded first. Now, what is this f of n? Okay, so this is basically a evaluation function, right? Now, based on this f of n value only, we discuss based on this evaluation function value only, we expand our node which is having the lowest evaluation being expanded, right? So lowest value of this particular function will explore that node first, right? The evaluation function is based for search is often a cost estimate and it determines search strategies. Okay, it includes a heuristic function h of n which estimates the cost to reach a goal state from the current node. So that's what I said. The heuristic cost associated with the particular node is from the current node to the goal state, right? In the case of uniform cost search, we have the cost from the start, not from the goal. But here we know, okay, if I go by this particular node, so A to G, it will take me 7 unit, right? B to G, it will take me 3 unit. I suppose it is C and D, right? And we have here we have a lot more nodes. And say for example, D to G, it will take around 8 units. So some kind of information is there from that particular node to the goal state, right? That is what heuristic is. Now, heuristic functions are a common way to provide problem-specific knowledge to a search algorithm, and they have typically non-negative and state-dependent, right? So, same thing. The heuristic function must satisfy the constraint. If a node is a goal state, the heuristic value is 0, right? So, in the case of uninformed search, we start from a initial state that is a value of this 0, but in the case of informed search, we consider the heuristic value of this particular goal state is 0. This is very, very important concept, right? This is very, very important. The heuristic value of a particular goal state is considered as 0. Okay, the heuristic value of a particular goal state is considered as 0. So very important point. Okay. Now, base first search guided by heuristic information can significantly improve search efficiency compared to uninformed search strategies that can be adapted to various problems and domains. Yeah, that's the case, because in the case of uninformed search, we are exploring all the nodes. But in this case, okay, we know if I go by this particular node, then it will take less number of time, less number of cost, less cost, right? So we'll not explore this particular path. So we don't need to explore each and every node in this case, right? So this is some advantage of informed search, right? Now there are two types of informed search. First one is best first search algorithm, that is greedy search, and we are going to discuss about A star search algorithm. So greedy search and A star search algorithm both are the types of best first search algorithm only, right? The only difference is that is the evaluation function. Now let us consider three functions. First one is evaluation function, right? This is evaluation function. So based on this particular value of a node, we expand our node. Which one is having the lowest cost? So this is basically an evaluation function. Now h of n is basically a heuristic function, right? Heuristic function. Now consider one more function, that is g of n, right? So it's basically a cumulative cost of node n from start node. Okay, this is very important. Start node, that is S. Here heuristic function is basically the cost or any value from a particular node to goal node, that is G, right? So it distance from a particular node to a goal, and this Gn is basically a cumulative cost of a node from a node n from a start node, right? So please keep a note of this three particular function. Now what happened in the case of greedy search? My value of evaluation function is basically a h of n only, right? So in the case of greedy search, our search algorithms solely depend on heuristic value. It doesn't matter how much the path cost is, we only dependent on the heuristic function. right? Okay, let us take one example. Suppose this is my this is my node A, this is B, this is C, this is suppose D, this is E. Okay, I'm going E and then we are going to F. Okay, so A is my initial node, F is my goal node. Okay, and suppose this is my cost associated with each path, right? Now in this case, what happening? If we apply greedy search algorithm, right? We do not care about the past cost of each of the path, right? We only place with the heuristic function, right? H of n value. Now that H of n value, how it is calculated? Now this H of n function is basically any function. It will be given in the your problem, or generally it is considered as a straight line distance. So straight line distance, we are considering straight line distance or Manhattan distance, okay? Or Manhattan distance, or it can be any expression based on which we will determine the heuristic value. Okay, so it may be given in your question, right? Now what is straight line distance? Suppose I want to go from node A to F, right? And from A I can go to B and C, right? But I will not consider this particular cost. What I will do, if I know, okay, from B to F I will require 4 unit, from C to F I will require say 5 unit, right? And they say D to F I have 6 unit, and say E to F I have say 3 unit. Okay, this is my heuristic function. This is my H of n value from this particular node to the goal node, right? For each of the node B, C, D, E, this is my heuristic value, because heuristic function will cost from heuristic function is basically a cost from a node, from this particular node to a goal node, right? Now in this case, what happens? Even if this particular cost is low, but I will compare. If I go by node B, then it will take me 4 unit. If I go by node C, it will take me 5 unit, right? So we have open list and we have closed list, right? Close it. So open is basically my frontier and close is basically my explore state. So first I have open A, but from A I can go to B and C, right? So I will close A, I will go to B and C first. But what is the heuristic value of B and C? From B it will take me 4 unit, and from C it will take me 5 unit, right? So I will go via B, because B is having the less heuristic cost, right? So I will go through B. Now I will decide from B I can go to E, but what is the cost associated with E? E to F, that is 3, right? So I will remove B, I will add in closed state, I will add B here, right? Now cost associated with E to F is 3. Now here also, now you need to compare between C and E, right? Now from C it will take me 5 unit, and from E it will take me 6 unit. Okay, now from E I can directly go to F with a cost of 3, right? So that's it, we will find out the code. But what if suppose this is my 6? Okay, this will take around 6 cost. Okay, now in this case what happens? E is 6, right? But C is less than this particular node 5, right? The value of the heuristic value of C is less than this particular node E. Then in that case what happens? It will stop searching this particular path, then it will move on. Then our search algorithm will move on this particular path, right? So C, it will explore C because it is having the least cumulative cost. From C it can go to D, that is D, this 6 only, right? So either of the node you can take to reach the particular uh, goal state. So in short, what I want to say, it will consider only the heuristic value, not the path cost in the case of greedy search algorithm, right? So that's the thing. So this is what f of n equals to h of n. Now in the case of A star algorithm, what happens? The evaluation function will become g of n plus f of n. So based on this f of n value, which one is having the lowest cost, we'll take that particular node, right? Now here g of n is basically, so this h of n, okay? Now g of n is basically a cumulative cost of node from start node S, and f of n is basically from that particular node to goal node, right? Now let us take this particular node D. The cumulative cost for this particular D is 2 to 3, that is 5, right? To reach this particular node. But from this particular node to reach till F, I have heuristic value of 6, that is 6. So I will add 6 here, so that is 11, right? Same thing I will compare for E also, for B also, for E also. For E it will take me 1 plus 2, 3 plus the heuristic value, that is E2F, that is 6, that is 9. Okay, so 9 or 11, which one is less? So this is 9, so it will go by this particular route. So we'll discuss this in detail, A star search algorithm, in a different video in the next video, but our focus is on greedy search in this particular video. Okay, so I hope you understand this particular scenario. The difference between these two algorithms is the evaluation function. We have h of n. In the case of greedy search, it is completely based on heuristic value. In the case of A star search, we also consider cumulative cost of a node along with the heuristic function. Right, now let us take one more example. Now let us take one good example, that is maze example, that what we have. So same example we have discussed during DFS and BFS, right? So this is what we have discussed first, like search algorithm that expands the node that is closest to the goal as estimated by the heuristic function, right? It solely depend on the heuristic value of this particular node, right? So this is what greedy best first search is. So we have discussed this. Now let us take this particular example, right? Now what is heuristic function, right? This is my starting point, this is my ending point. Okay, I know I need to go from this particular A to B, right? The same thing we have discussed during BFS and DFS lecture also, right? So you can watch that particular videos, okay, before watching this particular video, right? So what is heuristic function here? How we can determine a heuristic function in this case, right? Suppose I have 2 points, that is C and D. Okay, now as a human, by looking at this particular graph or state space, I can say, okay, if I go if I go through C, it will take me more time. If I go by D, it will take me less time, because D is geographically closer to B, right? I can see with my eyes that D is geographically closer to me. It is closer to our goal set, that is B, right? So in this case, what I will do, I will skip this particular point C and I will go through D, because I know this D is geographically closer to B. We don't know the goal state, right? We don't know the goal state, but we know something, because we know some information about the particular goal state. If I go by D, it will take me less time rather than going by this C, right? So this is what heuristic function is. Now as a human, I can say directly, okay, this particular point is closer to this particular goal, but how algorithm will decide? So that is based on the heuristic function h of n, right? Now what is heuristic function in this case? That is Manhattan distance, that is h of n, right? So simply here you can see, assume that there are no restrictions, okay, of following the path. So simply it is a difference in x coordinate plus difference in y coordinate, right? That's what the distance is, this Manhattan distance, right? So if I go by like this, or if I go to D like this, so value of D will be less, right? The Manhattan distance of this particular point will be less, so I will go through this particular point. Now for this particular example, we are considering Manhattan distance as my heuristic function value, okay? Okay, so this is the starting point A, this is the my goal state A, and this is the Manhattan distance, like from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So I am 16, say, points or unit away from my particular goal. I am 12 unit away from my particular goal. I am 8 unit away from particular goal. So this is what heuristic value is given, right, uh, for each of the location, right? Now we start searching from A. So as we know, we don't have any path to follow, so we'll keep following this only one path. Now this is my decision point, right? So this is my decision point 12. Now either I can go on left or right. So in the case of DFS, which we decide to go on the left side, we'll explore all the path, then we come back. In the case of BFS, we explore both the paths simultaneously. But here what we are doing based on the heuristic value, right? So 11 is less, so I will go through this particular path, that is 11. So I will going, I am following this particular path, 11, 10, 9, 8, now 7. Now in this case, I can select anyone, like I can go straight or I can go on the right hand side, but let us go straight. So I didn't found any goal after this particular path. Then I will say which one is having the lowest heuristic value. So in this case it's 7 and here it is 13. So definitely I will follow this particular direction, right? Then I am going through 7 and 6 and 7. Okay. Now again here you can see, right? Again here you can see we have a lesser value of 6 here and 8 value of here. Always we follow lower heuristic cost. So I will go to 6, 5. Now in this case you can see, right? Now here you can see I can go up or I can go down, but based on my heuristic value, I will always go up, right? Because it is lesser, so I will going up 4, 3, 2, right? Here you can see I don't have any specific. Here we can say I reached a dead end, I didn't found a particular goal. right? But now we have three options: this 6, this 8, and this 13. Now in this case, which path I will follow? Basically, which is having the lowest heuristic cost. So in this case is 6, so I will follow this 6. Now I have this 7 and this is 8, right? So 7 is less than 8, but I will continue to follow this particular path, and finally I will reach this particular. Now this is the path what greedy first search algorithm will follow, right? So based on the heuristic value, it will follow that particular path. I hope this example makes sense. Okay, I hope you understand this particular example. Okay, but whether it will give me an optimal solution, is an optimal solution or not, whether greedy first search will give me optimal solution or not. In this case, you can see, okay, if I go by this particular part directly, it will give me optimal solution. I don't need to explore this, I don't need to explore this, right? But whether it will give me a optimal solution or not, this is something what we have to discuss, right? Now let us consider this example, right? Same example, but we have changed the configuration. So we are considering Manhattan distance as a heuristic value here. So if I go by like this, so it will take 16 units. If I go by like this, also it will take around 16 units, right? Now if you observe, I will go like this, like this. I will go like this, like this, because 13 is less than 11. So I will continue to follow this, right? Like this, 7, 9, 10, 11, 12, because 13 is greater than this 12, right? The same thing I will follow, right? Because not a single particular node is greater than the 13, right? So basically I will follow this particular path and I will reach this goal state, right? So this is what this path is. But this part is optimal or not? We got the solution, right? But this is not the optimal solution, right? If we follow this particular path, right, this will be an optimal solution from these two solutions, right? But what greedy first search has done, they have followed this particular path based on a heuristic value. So the performance of greedy first search will depend on the heuristic value, heuristic function. Okay, if you select a good function heuristic value, if you select a good heuristic value, then it may give you the good path. May not be optimal path, but good path, not the worst one. But if your heuristic function or value is not accurate, then it may give you the worst case scenario also, right? So that's the thing. So greedy best first search will not give us the optimal solution, right? Because this is the optimal solution, right? Not this. Okay, I hope you understand this particular example. Now let's discuss some important points. So greedy best first search relies solely on heuristic value, that is h of n, to evaluate the nodes and select the one closest to the goal, right? Aiming for a quick solution. Heuristic value like straight line distance or Manhattan distance, right? It depends, cannot be deduced from a problem description alone and may require domain specific knowledge. Yes. So based on domain specific knowledge only, we find out the heuristic value. The greedy best first search is not optimal and may not always find the shortest path. So this is what we have discussed. But as it prioritizes the nodes that seems closest to the goal, right? In some cases, greedy based first search can become incomplete also. So this is incomplete and this is not optimal, leading to infinite loops when dealing with the certain state spaces, right? So that's it from this particular search algorithm, that is greedy based first search algorithm. In the next video, I am going to take one example, okay? One example based on a greedy based first search, okay? That is a tree example. So what we have discussed during all the uninformed search, so it will be better if we discuss that one example, right? So that's it from my side. Thank you.